Okay, so we'll start a new chapter, chemical bonding. So in this chapter, chemical bonding and molecular structure, we'll go through different types of uh, ideas that are involved in describing or in generalizing bonding in chemistry. So this is an important highlight of the subject itself. Now, in your syllabus, it's given as the distribution is given as valence electrons, ionic bond, covalent bond, bond parameters, which we will exclude, Lewis structure, polar character of covalent bonds, covalent character of ionic bonds, valence bond theory, resonance, geometry of various molecules, Vesper theory, hybridization, and so on. Now, um, to start with, what are valence electrons? What are valence electrons? Now, from the previous chapter, we know that how to write the electronic configuration for various elements. Now, suppose, for example, carbon. For carbon, we know that carbon its atomic number is 6. That means it has 6 electrons. So 1s2, 2s2, and 2p2. So here, the last two orbitals gives you the number of valence electrons or valency of that particular element. For example, boron. Boron, we know the atomic number is 5. So 1s2, 2s2, and 2p1. So this is the valence. So the valency of boron is 3 and the valency of carbon is 4 and so on. Suppose if it is oxygen, we know oxygen is 8. So 1s2, 2s2, 2p. So the valency of oxygen is 6 and so on. So these are examples of valence electrons. Now, these valence electrons are responsible for making, or the valence electrons make up the bonds in between different atoms. But so let's move on to ionic bond. What are ionic bond? There are different types of bonds, like the covalent bond, the ionic bond, and so on. Now, metal-metal bond is also there. So, what are ionic bonds? So, these ionic bonds are formed as a result of distribution of charges, or suppose when we say sodium chloride, a common salt. So, sodium has positive charge and chlorine has one negative charge. So when these two combines, they give us sodium chloride. And these, if they are made up of charges, if the bonding between two atoms are made up of charges, then we call them as, or they are ionic bonds, or ionic elements, or ionic compounds. But if they are made up by sharing electrons, suppose in the case of water, H2O. So here we know oxygen has 6 valency. Now hydrogen has 1 valency. So hydrogen will share with the oxygen and this will form a bond. This will form a bond, and now the octet configuration of oxygen is achieved. So these type of bonds are called covalent bonds. Covalency. They satisfy each other valency. Therefore, they are called covalent compounds, and they are formed by sharing of electrons amongst themselves. So that is an example of covalent bond. So to represent covalent bonds, Gilbert Newton Lewis, he devised a technique called the Lewis structure. Now, I've already shown you one, the formation of water. Like oxygen, as we know, have six valence electrons, and hydrogen has two electrons, one electron each. So this is the representation of water molecule in terms of Lewis structure, Gilbert Newton Lewis structure. So we place the central atom first, and then we add the covalency. We generate the structure likewise. Suppose, for example, this is for water. Another example, we'll take oxygen. So for oxygen, so the oxygen molecule, the Lewis structure is represented this because, see, for example, this one, uh, these two electrons will share and then make one bond. Similarly, these two electrons will share to make one bond. But for here, there are four electrons in between them, which suggests that in between the oxygen atoms we have two bonds. So that is how Lewis structure is determined by the valency of each of the respective atoms. Suppose, for example, chlorine molecule. Now we know chlorine has one valency. So, sorry, chlorine has one valency, 1, 2, 3, 4, 5, 6, and 7. So another chlorine atom will share one electron amongst themselves. So their octet configuration is satisfied here also. So this will give us, since we have only we have only two atoms in between them, so chlorine has only a single bond. So that's how we determine the structure of various covalent bonds. So you can try out for nitric acid, sulfuric acid, nitric acid. Those two are your assignments. Okay, now to describe chemical bonds, there are different theories. First one is the octet rule. Octet rule. The second one is our valence bond theory. Valence bond theory. Third one we have the valence shell electron pair and repulsion theory. This theory, and the fourth one is our molecular orbital theory, and now it's not included in your syllabus, but these are the upgrades, just like upgrades from the first one was octet rule. From there, because of some anomalies, valence bond theory was adopted, and with certain modifications, valence shell electron pair repulsion theory came about, and then an upgrade of that was molecular optical theory. This is the quantum approach, and then another one is there, adjusted, uh, where we call crystal field theory, or adjusted Ligan field theory, or simply Ligan field theory. And then this is molecular orbital theory, is the quantum approach. So these are some of the theories that tries to describe the nature of chemical bonds. Now we'll go one after the other. So let's try to focus first on the octet rule. What is, or what do we mean by octet rule? So there is a tendency in each atom. Of course, we know that atoms don't exist independently. They combine with other atoms and form molecules, and they exist in that way. But there is a tendency of each atoms to have to be fully filled or have 8 electrons in the outermost shell, and that is known as the Lewis octet theory or Lewis octet rule. Suppose, but suppose in terms of hydrogen, we have only one s orbital, where we have only one electron. So the octet rule would be like the hydrogen wants to have 2 electrons in the outermost shell. That is the outermost shell of hydrogen. So it wants to have 2 electrons to be more neutral or to be stable. Likewise, for example, oxygen. Oxygen, we know it has 6 valence electrons, whereas 2 to be 4. So it has 6 uh, valence electrons, but it wants to have 8. That means 2 needs to be added more in order to achieve that octet configuration. That's what the octet rule suggests. So to achieve that, they share with other atoms. Like in case of water, it shares, the oxygen shares with 2 water molecules, so that each water molecule, each hydrogen atom also gets one electron from the oxygen atom, making it fully filled, and then the 2 hydrogen atoms will share with oxygen, making it fully filled, or octet configuration. That's what octet rule is all about. But in terms of the octet rule, there are some limitations, of course, such as the odd electron molecules, like suppose nitrous oxide and all, where the you'll see that if you try to make the Lewis structure, it's one of the atoms will not be satisfied with the, or nitrous dioxide, one of the atoms will not be in compliant with the octet rule. That means, suppose if we draw the nitrous oxide, oxygen. So here, this oxygen is not fully satisfied. That means it doesn't fully, it is not obeying the octet rule. So there are some limitations to the octet rule, like the incomplete octet of the central atom. Sometimes it happens, and the expanded octet, there are certain instances where the central atom has more electrons than what actually is required. Suppose phosphorus pentachloride, sulfur hexafluoride, and as in case of sulfuric acid, if you do the Lewis dot, then you'll find out that there are 12 electrons surrounding the sulfur atom. So, like, these are some of the limitations of the octet rule. So, in order to counter that, valence bond theory was adopted. But before moving on to valence bond theory, let's try to understand the concept of resonance. So, what do we mean by resonance? So, as we have found out some of the one of the limitations of octet rule, that some of the molecules, they don't obey the octet rule even though they are formed, like nitrous oxide, or for example ozone. Now in ozone also, in ozone we have three oxygens arranged this way. One, or simply put, the electronic configurations can be satisfied only with this arrangement, because it will be violating the octet rule. Therefore, it assumes this or adopts this structure. But as we can see that this double bond, it's when we look spectrophotometrically, then we'll see that this double bond doesn't behave as it has to be a double bond, or this single bond doesn't behave as a single bond. Meaning, in reality, these single bonds are longer in length than these double bonds, because double bond simply means that since four electrons are shared between these two uh, oxygen atoms, so they'll be more closer than these two oxygen atoms, because they are sharing only one electron each, so they'll be more farther apart. But when we measure spectrophotometrically, we observe that this doesn't behave truly as a double bond, and this doesn't behave truly as a single bond, but it's in between. These two are in between. For in reality, it has to be 1 to 1 picometers. Sorry, picometers, not micro. If it is double bond, and this has to be 148 picometers. But due to resonance, it is a hybrid in between. So it is no longer 121 picometers, but 128 picometers, and this one is also 128 picometers, which simply suggests that this double bond is distributed throughout the molecule. We can represent the resonance structure like this: double bond O, double bond O, and we have a lone pair here. So this goes in, and this lone pair comes. So the double bond shifts now to the other side of the atom. So again, this will reverse. This can reverse. So that is what resonance is all about. Now, in covalent bonds, we know that covalent bonds are formed from sharing of electrons between two atoms. Now, but sometimes covalent bonds acquire partial charges, like, for instance, hydrogen fluoride. It's a covalent bond. It is formed by sharing of sharing of electrons amongst fluorine and hydrogen. But we know fluorine is a very it is a very electronegative element. So what it wants to do is it wants to pull all the electron clouds towards itself. So once it pulls all the electron clouds towards itself, suppose these are the nuclei of hydrogen and fluorine. So we'll see that the electron cloud is being pulled towards the fluorine side, making it very negative and rendering the nucleus of hydrogen to be almost bare. So it acquires, because the nucleus is positively charged, it acquires slightly positive charge, and hence the fluorine is pulling all the electrons towards the side. It acquires slight negative charge, and so now it is polarized. Now it is polarized. So that is how covalent compounds assumes ionic character, because we know ionic bonds are formed by sharing of charges. Now, even if hydrogen fluoride is a covalent molecule, because of the electronegativity of fluorine, the molecule uh, acquires charges, and so it becomes polarized. And then this polarization is measured in terms of debye, or dipole. It acquires a dipole moment, and that dipole moment is measured in terms of debye, and we denote it with this arrow. This signifies the negative charge, and this signifies the positive end of that molecule. So that is the dipole moment of this particular hydrogen fluoride molecule. Now, this polarizability of different atoms is governed by something called Fajan's rule. Fajan's rule. Now, it's given in your book. I suggest you look at it. But Fajan's rule is dependent on, according to Fajan, the size of the cation and the size of the anion are a factor in determining the polarizability of a particular molecule. Like, for instance, the cation has to be small in size, like this. In case of hydrogen, the cation is very small, and the fluorine is much bigger compared to hydrogen. And then the size of anion is much bigger compared to size of cation. So those are some of the things that governs the polarizability of a particular molecule. Alright, now let's try to discuss something on valence shell electron pair and repulsion theory. Let's start here. Now we know about the Lewis dot structures and the how covalent bonds are formed by sharing of electrons. Now, according to this rule, valence shell electron pair and repulsion theory, uh, the shape of this Vesper theory, it gives you somehow an idea about the geometrical shapes of different molecules. Now, according to this theory, the valence electrons that are present in an atom, if they are if they are uh, if they are more than one valence electron, then they are pulled apart, or there occurs repulsion in between them. Suppose, for example, carbon. Carbon, we know its valency is 4. So there are 4 valence electrons. So carbon, in terms of when we think about carbon, the 4 carbons will be equally pushed apart. There will be equidistant from each other, and then when it forms when some other atoms come and forms bonds with it, it will be equal distance apart in forming the molecule. Suppose, for example, methane, CH4. So there will be 4 hydrogens that will be sharing electrons with each of the valence electrons of carbon. So methane will be like this. But since the atom is spherical in shape, so if you think about this structure, this is a two-dimensional structure, so it's a planar structure. But in reality, these 4 atoms, if you think about in terms of sphere, these 4 atoms will be somewhat placed like this, one behind the screen, with equal distance apart. Imagine an atom to be a sphere, a football, and then each of the 4 electrons arranged equal distance from each other. So this methane, it assumes a tetrahedral structure. So this is the real structure according to Vesper, and from the techniques that we have developed now, we now have proven the structure of methane to be tetrahedral. Tetrahedral. Now imagine a cube. To picture this tetrahedron, imagine a cube, and then you imagine these four dots to be, I'll use a different color, to be at opposite ends of that cube, and carbon is here. So hydrogen will come here like this. So now that is a tetrahedral structure. If you can picture it, the four valence electrons will occupy opposite corners, and then so that is a tetrahedral structure, and that is being predicted by whisper theory. There are lots of molecules that their geometric shapes has been predicted successfully by this whisper theory. Now, it's given even in your book, like according to Vesper theory, if there are only two valence electrons, then it assumes a planar shape. The molecule is planar, and if there are three valence electrons, then it will be like a triangle or trigonal planar. And then if it is four, as we have now seen, it's tetrahedral. If it is five, then it's going to be pentagonal pyramidal, bipyramidal, pentagonal, bipyramidal. Oh, sorry, not pentagonal, trigonal. Sorry. Diagonal, bipyramidal. And then if it is six, then usually it's octahedral. And then if it is seven, then pentagonal bipyramidal. Those structures, as well as different types of examples, are addressed in your book, so I suggest you go through, and then if you have any doubts, you can ask me again. So we'll start with valence bond theory in the next video.